Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 7, Real Airflow and Aerodynamic Testing. So far, we have often described airflow in clean, orderly terms. Air approaches a wing, divides around the leading edge, follows the surface, creates a pressure distribution, and leaves behind the aircraft in a controlled wake. That is a useful starting point. It is also incomplete. Real airflow is messy. It contains friction, turbulence, vibration, tiny disturbances, changing pressure, separation, gusts, rough surfaces, manufacturing imperfections, and interactions among every part of the aircraft. A wing that looks excellent in a simple calculation may behave differently in a wind tunnel. A wind tunnel model may behave differently from the full-size airplane. And even after extensive testing, the real aircraft still needs flight test before engineers can be confident that it behaves as expected. This lesson explains how engineers deal with real airflow. We will cover boundary layers, laminar and turbulent flow, transition, separation, Reynolds number, wind tunnel testing, flow visualization, computational models, flight testing, and uncertainty. The central idea is straightforward. Aircraft engineering is not based on one perfect equation or one perfect test. It is based on building confidence from several kinds of evidence. Ideal flow versus real flow. In an introductory aerodynamic calculation, engineers sometimes imagine air as having no viscosity. Viscosity is a fluid's internal resistance to shearing motion. In ordinary language, it is the tendency of a fluid to resist layers sliding past one another. Honey has high viscosity. Water has lower viscosity. Air has much lower viscosity than either, but it is not zero. That small amount of viscosity changes everything near an aircraft's surface. An idealized, inviscid airflow can wrap around a smooth wing or fuselage without losing energy to friction. It can predict broad pressure patterns and lift behavior remarkably well in many conditions, but it cannot properly predict skin friction drag, boundary layer growth, transition to turbulence, flow separation, stall, or many of the interactions that determine whether an aircraft is safe and efficient. Real aircraft operate in real air. The air has viscosity. It also contains dust, water vapor, temperature variations, turbulence, sound waves, gusts, and disturbances from the aircraft itself. The practical result is that engineers use idealized theory to understand first-order behavior, then add more realistic methods, experiments, and flight data to see what actually happens. A good analogy is structural design. A simple beam equation can predict whether a beam bends under load, but a real aircraft structure also has joints, fasteners, manufacturing tolerances, material variation, vibration, cracks, corrosion, and complex load paths. The basic theory matters, but it is only the beginning. Aerodynamics works the same way. The boundary layer, a thin region with outsized importance. The most important feature of real airflow near an aircraft surface is the boundary layer. The boundary layer is the thin region of air immediately next to the surface where viscosity matters strongly. At the surface itself, the air has nearly the same velocity as the aircraft surface. For an aircraft moving through still air, that means the air directly touching the wing is nearly motionless relative to the wing. This is called the no-slip condition. As you move outward from the surface, the air moves faster. Eventually, it reaches essentially the same speed as the undisturbed flow outside the boundary layer. Engineers commonly define the outer edge of the boundary layer as the point where airflow has recovered to about 99% of the free stream speed. You do not need to think of the boundary layer as a separate blanket of air. It is part of the overall flow, but it behaves differently from the air farther away because friction has slowed it. The boundary layer starts at the leading edge of a wing and grows thicker as the air moves toward the trailing edge. The same is true for a fuselage, tail, propeller blade, engine nacelle, landing gear strut, or drone arm. This thin region matters because it determines whether airflow can remain attached to the surface. If the boundary layer has enough energy, it can continue moving downstream even while the surrounding pressure rises. If it loses too much energy, it can slow down, reverse direction, and separate from the surface. That is the beginning of a stall on a wing, but separation can also occur on a fuselage, flap, engine inlet, landing gear fairing, or any other shape exposed to air. A boundary layer may be physically thin, but its behavior controls a large share of an aircraft's drag, lift, noise, control effectiveness, and stall characteristics. Laminar flow. Orderly and low friction. A laminar boundary layer is one in which air moves in relatively smooth, orderly layers. The motion still changes gradually from nearly zero at the surface to the free stream speed outside the boundary layer, but there is relatively little mixing across those layers. Laminar flow has an important advantage. It produces lower skin friction drag than turbulent flow. That makes it attractive for efficient aircraft. If a wing can maintain laminar flow over a large fraction of its surface, it can reduce fuel burn or extend range. But laminar flow is delicate. It can be disrupted by surface roughness, insects, dirt, rain, frost, or ice, caps, steps, dents, and protruding fasteners, vibration, turbulence in the incoming air, drum pressure changes, high angle of attack, manufacturing variation, control surface gaps, engine or propeller disturbances. A surface designed for laminar flow may need very high manufacturing quality and careful maintenance. A small imperfection near the leading edge can trigger early transition to turbulence, eliminating much of the expected drag benefit. Laminar flow is also more vulnerable to separation in an adverse pressure gradient. Since it has relatively little mixing, the slow-moving air near the surface does not receive much energy from faster-moving air farther out in the flow. This is why aerodynamic design sometimes faces a counterintuitive choice. Preserving laminar flow reduces friction drag, but encouraging transition to turbulent flow can help the boundary layer remain attached longer in a difficult pressure environment. The best solution depends on where the aircraft operates and what problem the designer is trying to solve. Turbulent flow. More friction, more energy near the surface. A turbulent boundary layer contains irregular, swirling, three-dimensional motion. It is not random in the sense of being unknowable, but it is much more complex than laminar flow. Turbulence mixes the air. Faster-moving air from outside the boundary layer exchanges momentum with slower air near the surface. That mixing gives the near-surface flow more energy. This has two major consequences. First, turbulent flow creates more skin friction drag than laminar flow. The extra mixing and shearing cost energy. Second, turbulent flow can resist separation better than laminar flow. The near-surface air has more momentum, so it is better able to keep moving downstream when it encounters rising pressure. That trade-off is central to practical aerodynamics. Imagine a wing surface where the airflow slows as it moves toward the trailing edge. If the boundary layer remains laminar too long, it may separate early. The separated flow creates a large drag penalty and reduces lift. In some cases, it is better to let the flow transition to turbulence earlier, accepting a modest friction drag increase in exchange for avoiding major separation. This is why some airfoils include small, carefully placed roughness elements called turbulators, or trip strips. Their purpose is to trigger transition from laminar to turbulent flow at a controlled location. The idea may seem strange at first. Intentionally create a small disturbance to avoid a much bigger problem later, but that is a common engineering strategy. A predictable, manageable loss can be better than an unpredictable and much larger failure. Golf ball dimples offer an everyday analogy. A smooth golf ball creates a boundary layer that can separate early, leaving a large wake and high-form drag. The dimples encourage a turbulent boundary layer, which stays attached longer and reduces the size of the wake. The ball flies farther even though its surface is rougher. An aircraft wing is much more complex than a golf ball, but the principle is similar. Friction and separation must be considered together. Transition. The change from laminar to turbulent flow. The process by which a boundary layer changes from laminar to turbulent is called transition. Transition does not happen at one universal location. It depends on speed, size, air density, surface condition, incoming turbulence, pressure gradient, temperature, and the shape of the body. On a smooth wing in calm air, the boundary layer may remain laminar for some distance from the leading edge. Small disturbances gradually grow. Eventually, the flow becomes unstable enough that it breaks into turbulent motion. On a rough or contaminated wing, transition may occur much earlier. On a propeller-driven airplane, propeller slipstream can alter the transition behavior over the wing and tail. On a jet aircraft, engine nacelles, pylons, and exhaust can create local disturbances. On a drone, exposed wires, camera mounts, battery compartments, arms, and motors can interfere with smooth flow. Transition matters because it changes skin friction drag, separation behavior, heat transfer, noise, and sometimes control effectiveness. It is not always obvious from the outside. A wing may look smooth and normal while its boundary layer has changed dramatically because of rain, frost, a small dent, or a manufacturing detail. Engineers often use sensors, flow visualization techniques, or specialized coatings to locate transition during testing. They want to know where the orderly flow ends, where turbulence begins, and whether the real aircraft matches their expectations. Reynolds number, comparing airflow across scale. One of the hardest parts of aerodynamic testing is that a small model and a full-size aircraft do not automatically behave the same way. A model airplane may look exactly like a full-size airplane, but if it flies at a much smaller scale and lower speed, the airflow around it can have very different boundary layer behavior. It may transition, separate, or stall differently. To compare flows meaningfully, engineers use dimensionless numbers. The most important one for many low and moderate speed aerodynamic problems is the Reynolds number. Reynolds number compares inertial effects to viscous effects in a flow. In plain language, it tells engineers whether the air's momentum or its frictional behavior is more dominant. A simplified form is: where is air density? Is airspeed? Is a characteristic length, such as wing chord? Is the air's dynamic viscosity? The exact formula is less important than the implications. Reynolds number increases when the aircraft or model is larger, the speed is higher, the air is denser. Reynolds number decreases when the model is smaller, the speed is lower, the air is thinner. Viscous effects are more influential. A small drone and a large airliner can both fly at the same speed, but the air does not behave around them in the same way because their characteristic sizes differ greatly. Small drones often operate at relatively low Reynolds numbers. Their wings and propellers may experience earlier separation, different transition behavior, and different aerodynamic efficiency than a full-size airplane wing. This is one reason small-scale aircraft design can be surprisingly difficult. Wind tunnel testing must account for this. A scale model may need to be tested at higher speed, higher density, or in a pressurized or cryogenic tunnel to achieve Reynolds number conditions closer to the real aircraft. NASA notes that wind tunnel force measurements often require correction or post-test data reduction to account for Reynolds number and Mach number differences between the model and full-scale aircraft. 1. Reynolds number does not explain every aerodynamic effect. Mach number is also essential when compressibility matters, but for boundary layers, transition, separation, and low-speed model testing, Reynolds number is a central idea. Flow separation. When air lets go, flow separation occurs when the boundary layer detaches from a surface. The usual cause is an adverse pressure gradient. This means the airflow is moving into a region of increasing pressure. The flow must slow down as it moves into that pressure rise. If the boundary layer has enough energy, it continues following the surface. If it does not, the near-surface flow slows to zero and can reverse direction. The outer airflow then peels away from the surface. Behind the separation point, the flow becomes recirculating, turbulent, and inefficient. Separation can cause loss of lift, increased drag, buffet and vibration, reduced control effectiveness, unsteady aerodynamic loads, increased noise, changes in pitching moment, engine inlet distortion. Stall. On an airfoil, separation often begins near the trailing edge as angle of attack rises. As the angle increases further, the separation point moves forward. Once enough of the upper surface is separated, lift peaks and then falls. That is a stall. But separation is not limited to wings near stall. It can occur around flaps deployed too far, landing gear components, fuselage sections, engine nacelles and pylons, helicopter rotor blades, propeller blades, control surfaces, drone arms and payload mounts, air intakes, external fuel tanks, antennas and sensors. A vehicle can have attached flow on most surfaces and separation on one small component. That local separation may produce more drag, noise, vibration, or heating than expected. Engineers often spend significant time fixing these small issues because minor aerodynamic losses can matter over a fleet's operating life. Separation bubbles. A more subtle flow problem. Sometimes airflow separates, becomes turbulent, and then reattaches farther downstream. The separated zone between detachment and reattachment is called a separation bubble. A separation bubble can be stable and relatively small, or it can become unsteady and problematic. Laminar separation bubbles are especially relevant for small aircraft, drones, wind turbines, and low Reynolds number wings. A laminar boundary layer may separate, transition to turbulence within the separated region, gain energy through mixing, and then reattach as a turbulent boundary layer. This can create abrupt changes in lift and drag as speed or angle of attack changes. The aircraft may feel less predictable than the simple textbook airfoil model would suggest. The topic matters because many modern unmanned aircraft are small enough that low Reynolds number effects are central rather than peripheral. A wing optimized for a large airplane does not necessarily scale down well. Roughness, contamination, and real-world surfaces. Wind tunnel models often look pristine. Real aircraft rarely stay that way. A working aircraft may encounter insects on the leading edge, rain and water droplets, dust and sand, salt spray, frost, snow or ice, paint wear, repairs and patches, misaligned panels, loose seals, damaged fairings, oil or hydraulic fluid residue, manufacturing variation. Some of these conditions increase drag only slightly. Others can significantly change stall behavior. Ice is particularly dangerous because it changes both shape and surface roughness. Even a thin, rough layer near the leading edge can force early transition, reduce maximum lift, increase drag, and cause separation at lower angle of attack. This is why de-icing is not simply about removing visible chunks of ice. A wing must be aerodynamically clean. The aircraft's certification data and performance calculations assume a particular surface condition. Contamination can invalidate those assumptions. For long-endurance drones and remotely operated aircraft, surface condition is also a maintenance concern. A vehicle that spends months outdoors or repeatedly operates in dust, rain, agricultural chemicals, or salt air may gradually lose aerodynamic performance. The change can be subtle enough that an operator notices only reduced endurance or slower climb. Wind tunnels, bringing the air to the aircraft. A wind tunnel is a facility that moves controlled air around a stationary model, component, or full-size aircraft. Instead of flying a wing through the air, engineers hold the wing still and move the air past it. The important quantity is relative motion. The wing does not care whether it moves through still air or air moves past it. What matters is the airflow relative to the wing. Wind tunnels vary enormously in size and capability. Some are small tabletop facilities used to test model airplanes, drone propellers, airfoils, or student projects. Some are huge national facilities capable of testing full-scale aircraft components. Some operate at low speed. Others simulate transonic or supersonic conditions. Some are pressurized, refrigerated, or specially designed to achieve high Reynolds numbers. A typical wind tunnel has several main parts: a fan, compressor, or other system that moves the air, a settling section that reduces unwanted turbulence, screens or honeycomb structures that straighten the airflow, a contraction section that speeds and smooths the flow, a test section where the model is installed, a diffuser and return path, in closed-loop tunnels that slows and recirculates the air. The goal is not merely to blow air at a model. The goal is to create known, controlled flow conditions. Engineers care about the quality of the flow in the test section. Important qualities include uniformity, whether speed is nearly the same across the test section; steadiness, whether flow conditions remain stable over time; turbulence intensity, how much unwanted fluctuation exists in the incoming flow; flow angularity, whether air is truly moving in the intended direction. Wind tunnels remain essential because even advanced computer models have limits, especially in complex regimes involving separation, transition, turbulence, moving controls, shock waves, engine integration, and unsteady flow. 2. Force balances, measuring lift, drag, and moments. One of the most direct wind tunnel measurements uses a force balance. The model is mounted to a device that measures aerodynamic loads. The balance can measure lift or normal force, drag or axial force, side force, pitching moment, rolling moment, yawing moment. A force balance is essentially a very precise multi-axis load sensor. The model may be tested across a range of conditions: different airspeeds, different angles of attack, different side slip angles, different flap settings, different control surface deflections, different landing gear positions, different engine or propeller settings, different configurations of external equipment. The result is not just one value for lift or drag. It is a map of how forces and moments change across the aircraft's operating envelope. NASA describes force balances as the standard means of directly measuring aerodynamic forces and moments in a wind tunnel, including lift and drag. 1. Those measurements are essential for performance prediction and stability and control analysis. Engineers need to know not only how much lift the wing makes, but also how the entire aircraft responds if the elevator moves, a flap deploys, the aircraft side slips, or one engine produces more thrust than another. Pressure taps, mapping the invisible pressure field. A pressure tap is a very small hole drilled into the surface of a model or aircraft component. It connects through tubing or internal passages to a pressure measuring device. By placing many pressure taps across a wing, engineers can map the pressure distribution over the surface. This lets them answer questions such as, where is suction strongest on the upper surface? Is the pressure recovery too abrupt? Is a flap producing the expected lift increase? Is flow separating near the trailing edge? Is an engine inlet recovering pressure efficiently? Does the pressure pattern match computational predictions? How does the pressure change as angle of attack changes? Pressure data can be converted into estimates of lift and pitching moment. It also reveals the aerodynamic story behind a force balance measurement. Suppose a force balance shows less lift than expected. Pressure taps might reveal that upper surface suction is weaker near the leading edge, or that flow separates early near a flap. The force measurement tells engineers that something changed. The pressure distribution helps explain why. NASA notes that wind tunnel models can use pressure taps to calculate component performance, while total pressure probes are commonly used to assess engine inlet performance. 1. Flow visualization. Making air visible. Air is invisible, so engineers use methods that make its motion visible. Flow visualization does not replace quantitative measurement. It complements it. It helps engineers see patterns that a table of numbers may not reveal quickly. Common techniques include smoke streams, surface tufts, oil flow visualization, dye or vapor methods in special facilities, laser light sheets, pressure-sensitive paint, Schlieren imaging for shock waves, shadowgraph imaging for density changes, particle image velocimetry, often shortened to PIV. Smoke and vapor. Smoke or vapor introduced upstream can reveal streamlines, separation regions, vortices, and wakes. If the smoke follows smooth paths over the wing, the flow is likely attached. If it suddenly lifts away, oscillates, or forms a broad chaotic region, separation may be present. Smoke is especially useful for demonstrations because it makes the invisible intuitive, but engineers must be careful. The smoke must faithfully follow the flow, and the added material must not disturb the aerodynamic condition too much. Tufts. Tufts are small pieces of yarn or thread attached to the surface of a wing or fuselage. In attached flow, the tufts generally lie in the direction of airflow. In separated or reversed flow, they flutter, point in inconsistent directions, or move forward. Tufts are simple, inexpensive, and surprisingly useful. They are common in flight testing because they can reveal separation patterns on the actual aircraft. Oil flow. A thin film of oil mixed with pigment can be applied to a surface. As air flows over the surface, it moves the oil, leaving streaks that reveal local flow direction, separation lines, attachment lines, and areas of recirculation. Oil flow patterns can show whether air is moving smoothly toward the trailing edge or whether it is being pushed sideways, curling into vortices, or separating. Schlieren and shadowgraph methods. At high speeds, shock waves create abrupt changes in air density. These changes bend light slightly. Schlieren and shadowgraph optical systems use that effect to make shock waves visible. These methods are especially valuable in transonic and supersonic testing. They help engineers see where shocks form, how they move as Mach number changes, and whether they interact with boundary layers or control surfaces in undesirable ways. NASA lists smoke, laser sheet methods, surface oil flow, Schlieren, and shadowgraph techniques among the standard visualization tools used in aerodynamic testing. 1. Computational fluid dynamics. Powerful, not magical. Computational fluid dynamics, or CFD, uses computers to solve approximations of the equations governing airflow. Instead of building a physical model first, engineers create a digital representation of the aircraft and divide the surrounding flow field into many small cells. The computer calculates pressure, velocity, temperature, density, and other quantities in and around those cells. CFD is incredibly useful. It can help engineers explore many shapes quickly, predict pressure distributions, estimate lift and drag, study flow around complex geometry, examine engine inlets and exhausts, optimize wing shapes, investigate cooling flows, predict shock wave locations, model propeller wash, assess changes before building hardware. But CFD has limitations. The equations of fluid motion are known, but turbulence and transition are difficult to predict accurately in every situation. Engineers must make modeling choices about turbulence behavior, surface roughness, transition location, moving parts, and boundary conditions. A CFD result can look visually convincing while still being wrong in a crucial way. A colorful pressure image is not proof. That is why CFD results must be validated. Validation means comparing predictions against trusted experimental or flight data. A common workflow is: use simple theory to estimate what should happen. Use CFD to explore geometry and identify promising designs. Test models or components in a wind tunnel. Compare wind tunnel results with CFD predictions. Improve the model or revise the design. Test the actual aircraft in flight. Update the performance and control data using real measurements. The methods support one another. CFD can reduce the number of physical tests needed. Wind tunnels can reveal flow effects that CFD missed. Flight testing captures the full vehicle in its real operating environment. Wind tunnel limits and corrections. A wind tunnel is not the sky. The tunnel walls can influence the flow around the model. If the model occupies too much of the test section, it can block the airflow and artificially increase speed around the model. This is called blockage. The walls can also interfere with the model's wake, vortices, and pressure field. A finite test section cannot perfectly reproduce an infinite atmosphere. The model support system can add drag or alter the flow. A mounting strut may affect the tail or fuselage. Instrumentation wires, pressure tubes, and sensors can create small disturbances. A scale model may not match the full aircraft's Reynolds number. It may have different surface roughness. It may not flex the same way. It may omit details such as antennas, gaps, hinges, cooling inlets, or landing gear mechanisms. Engineers account for these effects using corrections, careful test design, repeated measurements, comparison among facilities, and full-scale tests. This is why good engineering is cautious about test results. A measured number is not automatically the truth. It is an observation with uncertainty, made under known conditions, using a particular model and measurement system. Uncertainty, calibration, and repeatability. Every aerodynamic measurement has uncertainty. A pressure sensor may have a small offset. A force balance may drift with temperature. The tunnel airspeed may vary slightly. The model may not be aligned perfectly. A control surface may deflect by a fraction of a degree more or less than intended. The air in the tunnel may have more turbulence than expected. Engineers manage this through calibration, repeated tests, instrument checks, controlled test procedures, data filtering, error analysis, comparison with independent measurements, documentation of test conditions. Calibration means comparing an instrument against a known standard and correcting its readings, if necessary. Repeatability means getting closely similar results when the same test is run again under the same conditions. Reproducibility means another team, facility, or instrument can obtain similar results using the same method. If a wind tunnel measurement shows a tiny drag improvement that is smaller than the measurement uncertainty, engineers cannot confidently claim that the change is real. They may need more tests, better instrumentation, or a larger design change. This discipline matters because aerospace decisions can be expensive. A small aerodynamic improvement may justify a major redesign only if it is real, repeatable, and meaningful in service. Flight testing. The final reality check. Wind tunnels and CFD are valuable, but the actual aircraft still has to fly. Flight test is where engineers observe the full-scale vehicle in real atmospheric conditions. The aircraft is fitted with instrumentation that can measure airspeed, altitude, attitude, acceleration, control surface position, engine thrust or power, fuel flow, temperature, pressure, structural strain, vibration, control forces, aircraft response to commanded inputs, navigation data, weather conditions. Test pilots and flight test engineers carefully expand the aircraft's operating envelope. They do not begin by immediately flying at maximum speed, maximum altitude, or maximum angle of attack. They start with conservative conditions and gradually test more demanding points as evidence shows that the aircraft behaves safely. Typical flight test questions include: does the aircraft take off and land as predicted? Does it stall in a controllable way? Are the control forces acceptable? Does it have enough pitch, roll, and yaw authority? Does it meet climb, range, speed, and endurance targets? Do flaps, gear, and spoilers create the expected changes? Are there vibrations, buffet, or flutter concerns? Does the engine installation behave correctly? Are there unexpected interactions between systems? Do actual fuel burn and drag match predictions? Flight tests also reveal real-world factors that are hard to duplicate perfectly in a tunnel. Atmospheric turbulence, rain, humidity and temperature variation, engine vibration, structural flexibility, pilot behavior, sensor noise, actual operating procedures, complete system interactions. The goal is not merely to prove that the aircraft can fly. It is to build reliable data for certification, pilot procedures, maintenance planning, performance charts, control law design, and future improvements. Validation, building confidence through agreement. A key word in aerospace is validation. Validation asks, does the model or analysis represent reality well enough for the intended decision? If a CFD simulation predicts a particular lift curve, wind tunnel data should broadly agree. If wind tunnel results predict a certain stall speed, flight tests should confirm it within expected differences. If the aircraft burns more fuel than expected in flight, engineers investigate whether drag, engine performance, weight, atmospheric assumptions, or measurement methods were wrong. Agreement among independent methods builds confidence. Disagreement is not necessarily failure. It is often where the most valuable learning occurs. Maybe the CFD model assumed fully turbulent flow, when the aircraft maintained laminar flow longer than expected. Maybe the wind tunnel had wall interference. Maybe the flight test aircraft had a surface imperfection. Maybe the engine installation produced more drag than the isolated engine test suggested. The engineering process is iterative. Predict, test, compare, understand, improve, test again. That cycle is how aircraft move from concepts to safe operational machines. A practical example: testing a new wingtip. Imagine engineers want to add a new wingtip shape to reduce induced drag. First, they use theory and CFD to estimate how the new tip might alter the wingtip vortex and improve lift distribution. Then they build a wind tunnel model. They test the original wing and the modified wing at different lift conditions, angles of attack, and sideslip angles. The force balance shows whether total drag changes. Pressure taps show whether the pressure distribution near the tip changes as predicted. Oil flow or smoke reveals whether the new tip causes unexpected separation. The engineers account for model scale and tunnel wall effects. If the results look promising, they install the wingtip on a full-size test aircraft. During flight test, they measure fuel flow, airspeed, altitude, and aircraft weight over carefully controlled conditions. They compare the modified aircraft with baseline data. The new wingtip may reduce drag, but it may also add structural weight, alter roll response, complicate manufacturing, increase maintenance cost, or create airport gate issues. The final decision depends on the whole system, not just one aerodynamic result. That is real aircraft development, a sequence of evidence-based trade-offs. Key takeaways: real airflow includes viscosity, friction, turbulence, transition, separation, surface roughness, and unsteady effects that idealized flow models cannot fully capture. The boundary layer is the thin region near a surface where air slows because of viscosity. Laminar boundary layers have lower skin friction but are relatively delicate and more vulnerable to separation. Turbulent boundary layers have higher skin friction but can resist separation better because mixing adds energy near the surface. Transition is the change from laminar to turbulent flow. It depends on size, speed, density, roughness, turbulence, and shape. Reynolds number compares inertial and viscous effects and is critical when comparing a wind tunnel model with a full-size aircraft. Flow separation occurs when the boundary layer can no longer follow a surface, producing drag, loss of lift, buffet, and potentially stall. Wind tunnels produce controlled airflow around stationary models or components. Force balances measure lift, drag, side force, and moments. Pressure taps map the surface pressure distribution that produces aerodynamic forces. Smoke, tufts, oil flow, laser methods, Schlieren, and related techniques make invisible flow patterns visible. CFD is powerful for exploring and optimizing designs, but it must be validated against physical tests. Wind tunnels have limits, including wall interference, support effects, scale effects, and measurement uncertainty. Flight testing is the full-scale reality check that verifies actual performance, stability, handling, structural behavior, and system integration. Aerodynamic confidence comes from agreement among theory, simulation, wind tunnel testing, and flight data. The next lesson, 1.8 Compressibility and high-speed flight, explains what changes when an aircraft approaches the speed of sound, why shock waves form, why swept wings are common on jets, and why transonic flight is one of the most demanding parts of aerodynamic design.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.